Welcome to this in-depth explainer on concurrency control in database management systems or DBMS. I am Chinmayam, and in this video we will break down what concurrency control is, why it matters, and the different techniques used to handle it effectively. This topic is essential in today's digital world where multiple users interact with databases every second, from booking tickets online to processing financial transactions. So let's get started with introduction to our topic. In a database system, multiple users and applications may access the same data simultaneously. This simultaneous access is called concurrency. While it allows for efficient and fast operations, it also creates a challenge. What happens if two people try to update the same record simultaneously? Without control, this could lead to a data corruption or incorrect outputs. So, concurrency is not just about speed, it's also about maintaining correctness, and that's where concurrency control comes into play. What is concurrency control? Concurrency control is the mechanism used to manage these simultaneous transactions. Its primary goal is to ensure that transactions are executed correctly, safely, in a way that the database remains consistent even when many operations are happening at once. This is achieved by maintaining the asset properties, particularly isolation and consistency. In simple terms, each transaction should behave as if it were executed alone, even if it runs alongside others. Example: two users try to transfer money from the same bank account at the same time. Concurrency control ensures balance is updated correctly. The goals of concurrency control. Let's talk about the main goals of concurrency control. First, correctness, ensuring data integrity no matter the transaction order. Next, serializability, the idea that the final result of concurrent execution must be the same as some serial execution. Deadlock freedom, prevent or resolve deadlocks to keep the system running smoothly. High performance, maximize concurrent options without compromising correctness. Let's explore the major techniques used to achieve concurrency control. First up, lock-based protocols. Locks are signals that prevent other transactions from accessing data currently in use. And timestamp based protocols, assigning timestamps to transactions and order operations accordingly. And optimistic concurrency control, allowing operations and validating before committing. Others, multi-version concurrency control, serialization, graph checking. Lock-based protocols. Locks are just flags associated with data that control how transactions interact. There are two types of lock-based protocols: a shared lock, which allows read-only access to multiple transactions, and an exclusive lock, which allows both read and write access, but only to one transaction at a time. Next up, we have a popular method here is two-phase locking. This has two phases: a growing phase where locks are acquired and a shrinking phase where locks are released. Once a transaction starts releasing locks, it cannot obtain any new ones. This structure helps ensure serializability. There is also strict two-phase locking, where all locks are released only after the transaction commits. This not only maintains serializability but also ensures recoverability. However, locks can lead to deadlocks, which we will cover shortly. And here we will learn advantages and limitations of lock-based protocols. Advantages: it works well in high conflict environments, easy to understand and implement. Strict two-phase locking ensures recoverability and cascading rollback avoidance. And limitations: it can lead to deadlocks if two transactions wait on each other's locks. It may result in low concurrency, that is, if too many locks are held together. It is complex to manage in large distributed systems. Example scenario: if T1 record A, T2 wants to write to A, but then T2 must wait. So let's move on to the timestamp based protocols. Here each transaction gets a unique timestamp, typically based on system time. Older transactions are given higher priority. If a newer transaction tries to overwrite data being used by an older one, it may be rolled back. The advantage: no deadlocks. The downside: more rollbacks in conflict heavy situations. Then there is optimistic concurrency control. This method assumes conflicts are rare, transactions proceed freely, and only check for conflicts at the end, that is, during the validation phase. If there's a conflict, the transaction rolls back. It's great fit for systems where reads far outnumber writes, like reporting dashboards or analytics platforms. Now, let's talk about one of the biggest challenges in concurrency: deadlock. Deadlock is a situation where two or more transactions wait for each other indefinitely. How to detect a deadlock situation? By using wait for graphs to identify cycles. And how to prevent deadlocks, that is prevention techniques: wait die method, wound wait method, and timeouts and deadlock avoidance algorithms. Example: resource ordering algorithm can also help to prevent deadlock situations. First, we need to understand what is a deadlock. A deadlock occurs when two or more transactions are waiting indefinitely for each other to release locks, and none of the transactions can proceed, leading to a standstill. Example: if transaction T1 locks A and needs B, transaction T2 locks B and needs A. Each waits for the other, creating a circular wait. In real life, we can understand it as when two cars are on a narrow bridge waiting for the other to reverse. So let's go to the next slide. Now, what are the deadlock conditions? Deadlock can occur if all four conditions hold simultaneously. First one, mutual exclusion. Only one transaction can use a resource at a time. Second one, hold and wait. A transaction holds one resource while waiting for others. No preemption. Resources can't be forcibly taken. Circular wait. A closed chain of transactions exists, each waiting for a resource held by the next. To prevent deadlocks, we can break at least one of these conditions. To detect deadlocks, we use a wait for graph. If this graph forms a cycle, we have found a deadlock. To recover, we might about one or two transactions to break the cycle. This decision can be eased on the age of the transaction and its priority and number of resources held, cost of rollback, etc. Circular wait, the root of the deadlock. A circular wait is one of the four conditions necessary for a deadlock. It happens when each transaction holds a resource and waits for a resource held by the next transaction. The chain of waiting forms a cycle, preventing all involved transactions from proceeding. Key idea: if you can break the circular wait, you can prevent deadlocks. Let us see an example of circular deadlock flow step by step. Let's visualize a circular wait. Imagine transaction T1 holds a resource A and needs B, and T2 holds B and needs C. T3 holds C and needs D. T4 holds D and needs A. This forms a cycle: T1 to T2, T2 to T3, T3 to T4, and back to T1. That's a textbook example of a deadlock caused by circular waiting. Breaking this chain prevents the deadlock. In this slide, we will see a real life example of concurrency control. Mm. Let's look at a real world scenario, an online ticket booking system. Imagine that there is just only one seat left. Two users, T1 and T2, both try to book it at the same time. Without concurrency control, both might see the seat as available and book it, leading to double booking and data inconsistency. But with proper concurrency control, one transaction blocks the seat record first, the second waits until the first is done. This ensures that only one booking goes through. What's the takeaway from this? So, concurrency control ensures correctness even when thousands of users access the system simultaneously. Concurrency control in modern databases. Concurrency control isn't just academic, it's everywhere. In banking systems, it ensures safe and accurate transfers. In e-commerce, it prevents overselling. On social media, it keeps updates consistent. And in cloud databases like AWS or Google Cloud, it's vital for handling millions of users. Modern databases like MySQL and Oracle use a hybrid of techniques to get the best performance and reliability. So, to wrap up, concurrency control is essential to ensure data integrity in multi-user environments. Concurrency control is a core component of any multi-user DBMS. Without it, we face serious issues like host updates and inconsistent data. Whether through locking, timestamps, or optimistic strategies, the goal is the same: the safe, accurate, and efficient transactions. Choosing the right method depends on the application requirements, such as read or write patterns, latency, and expected conflicts. So, thank you for watching.